Hi everyone, in this video we wrap up chapter 12 on trigonometric functions, right? We wrap up the chapter with the integrals of trigonometric functions, okay? So again, let's recall that taking the integral is the opposite of taking the derivative, right? Um, so here we are going to have a few formulas to integrate, right? To integrate trigonometric functions. Of course, we are not going to have all of them. There's many integral formulas. We're just going to go over the basic ones, right? Again, when we take the derivative of sine, all right, if we take the derivative of sine, what do we get? We get cosine, right? If we take the derivative of tangent, we get secant squared and so on, right? And we are going to have a few integrals, right, that are going to have answers in terms of natural logs, right? You'll see as we go along and we practice on this. All right, let's do basic example. We are going to integrate the function sine of 4x dx, okay? And by the way, let's make sure we have parentheses around the 4x, right? Again, because of the reason we mentioned on the previous video, right? All right, so in this case, we're going to do a u substitution, a very simple u substitution in which u will be the quantity inside of the trigonometric function, that is 4x, all right? So let's see, and then we are going to find the differential, du equals the derivative of 4x is 4 dx, all right? So that's the derivative, the differential, right? So let's rewrite the integral. So we're going to have the integral of sine of 4x. Okay, I'm going to leave a space here for that missing factor in order to complete the differential. All right, so with yellow, I'm going to highlight what we set for u, right? Which will be changed in the substitution, right? Now, in this case, when we take the differential du equals 4 dx, notice we are missing a factor of 4. We can, of course, put that factor of 4, provided we divide 1 out, all right? Again, what are we doing here? We are multiplying by 1, which is equal to 4 over 4, right? And then we can break up this 4 over 4 as 1/4 times 4, right? And we arrange this in a way that is convenient for all of us, right? In order to make the differential match, right? Now, what do we do next? Well, let me highlight with orange the part that will comprise, well, I think I need a different color here because it's not going to contrast with red. Let me see if this blue, it's not going to work very well either. What about green maybe? Not much. Purple. Okay, let's put purple, right? So when we do the substitution, guys, let's see. We're going to write 1/4 the integral of sine, right? The integral of sine of u, right? Because that's u, times du. Okay, again, let's highlight the corresponding u and du. All right. So this will be the same as 1/4 times the integral of sine. If we use the formula, if we look at the formula, let me scroll up to the previous page. The integral of sine will be negative cosine, right? Need to be careful when taking the derivatives and integrals of trigonometric functions because we know that the derivative of sine is positive cosine. However, the integral of sine is negative cosine, right? So need to keep that in mind, need to be careful with that, right? So we are going to have 1/4, right? 1/4 times negative cosine of u, all right? Plus c, don't forget the constant of integration, plus c, right? I'm going to take out this negative sign, 1/4 negative 1 4 cosine, and I'm going to do the back substitution instead of u. I'm going to write that as 4x, all right, plus c. And you might want to verify this result by differentiating, right? If you take the derivative of this, right? Take the derivative of that. What is the derivative of cosine? Isn't that negative sine? Negative sine of 4x, right? Times a mini chain rule, right? Times 4, which is the derivative of the quantity inside of the sine function. Right now, if we multiply 4 and divide by 4, these cancel. And then if we multiply negative times a negative, becomes positive. And what do we get as a final answer? Sine of 4x, which is exactly what we were integrating in the first place, right? You don't have to do this all the time, right? However, if we're just in case you're curious, just for fun, you may do, of course, right? Okay, let's do letter B. Okay, let's actually let me do letter C before I do letter B. I think we need more practice with it before looking at something more intricate, right? So let's do letter C. So for letter C, we have another integration of a sine function, right? So in this case, how do we choose the u and the du? Notice this is going to be u because this is one degree higher than what we have outside. However, let me rewrite this in a different way. Okay, I'm going to rewrite sine of x cubed times, I'm going to leave some space for that missing factor that we usually use, right? And x cubed dx, okay? All right, so what is going to be our u? Our u will be x cubed, and the du will be 3x squared dx, okay? Now, so we need to add that constant in order to compensate, right? So this is going to be our u equals x cubed, right? So on the substitution step, this x cubed will take the place of u, right? Or rather, u will take the place of x cubed. And in this case, we need a 3, right? In order to complete, provided we divide 1 out, all right? So this is going to be our du, right? This is going to be our du, okay? So this will be 1/3 the integral of sine of u du. Okay, that is, okay, highlight, see how x cubed becomes u only, and du becomes 3x squared dx becomes du. So all we have to do is, again, integrate sine the same way we did it on the previous example, right? So that'll be 1/3 times negative cosine of u plus c. And all we do now is back substitute for our u. I'm going to take out this negative sign in front of the constant, and cosine of, instead of x, I'm going to go back and substitute for x cubed, okay? Plus c. Don't forget your plus c. Okay. All right, let's go back to the example that I skipped. Okay, so let's see. Let's put this inside a bubble. Okay. Notice in this case, we have the product between secant and tangent. And by the way, this repeats 2x plus 1 and 2x plus 1. So that's what I will take as u. By the way, there's a little typo here. It should be an x, dx, not dt, okay? So, okay, let me erase this. I'm going to put on white, and I'm going to write my x myself like this, okay? There it is. All right, so I'm going to set u, the quantity 2x plus 1, and du which will be our differential here. Okay, that's 2 dx. Okay, I'm going to write the integral again because I need space here for that missing factor. So this will be the integral of secant 2x plus 1 tangent 2x plus 1 dx. All right, so when we compare, when we attempt to do the substitution, well, this will become a u on the next step, and here we need our dx, the 2dx become the du, right? So the thing is, in order to have this matching our du that I highlighted in purple, we need a factor of 2, but we can add that 2 provided we divide 1 out, right? So that will become 2dx, okay? So let's do the substitution now. So we are going to do 1/2 times the integral of secant of u times tangent of u, right? du. Okay, how do we integrate secant tangent? Let's go up to the previous page and notice this is one of the integration formulas, right? Secant tangent is, its integral is secant. In other words, if you take the derivative of secant, you get secant tangent, right? Just the same way we did it on the previous section. All right, so the integral, rather, not the derivative, the integral of this will be 1/2 secant of u. But what's u? Okay, don't forget the plus c. That's going to be 1/2 secant of 2x plus 1. Okay, and that is final answer for this exercise. Okay, let's move on to letter D. Okay, what about letter D? All right, so now we have a product of sines and cosines, and one of the trigonometric functions has a power, the other doesn't. But notice something. In this case, unlike the previous examples, for example, letter C, we use the u as the quantity inside of the parentheses of the trigonometric function. Now, in this case, u will be itself a trigonometric function. How come? Well, let me show the first few steps of this example, of this exercise. All right, so we're going to have the integral of, I'm going to rewrite this as sine of x to the 4th power, right, times cosine x dx. Okay, I need you to observe something. Do you notice this cosine dx will work really nicely as the derivative of sine, because the derivative of sine is cosine, right? And that we're going to accomplish that when we set whatever our u is and our du is. Okay, so I'm going to use a different color. Well, no, I'm going to stick to the same color rather. Okay, u equals sine. Du will be cosine dx. And in this case, notice the u, okay, the u, of course, this will always match, right? That's the purpose, right? The u substitution. However, notice in this case, right? Du will be taking the place of cosine x dx. Do you see how they match? In this case, no need to multiply and multiply by one constant, provided we divide one out of the integral, right? So we're going to have the following: the integral of u to the 4th du, and this is just an application of the general power rule, u to the 5th divided by 5 plus c. Okay, so we need to go back, substitute for u. So in this case, we're going to have sine of x to the 5th power divided by 5 plus c, or 1/5 sine to the fifth of x plus c. Okay. All right. Let's look at another example. Okay, let me put this inside a bubble. All right. Okay. The integral of e to the 3x cosine of e to the 3x. All right. First of all, I'm going to rewrite this integral, right? I'm going to write it as the integral, leave some space here for those missing factors. And this is going to be cosine of e to the 3x times e to the 3x dx, all right? So that's going to be our integral right here. All right. So in this case, notice how this e to the 3x, the derivative of the exponential, is not always itself, and the exponential times, well, whatever the derivative of the exponent is. So we are going to take advantage of that, right, to let our u equals e to the 3x. du equals 3e to the 3x, all right, dx. So what are we missing? Okay, first of all, let's highlight with yellow our u, all right, and then our du, first of all, notice we're missing a factor of 3. We can add it provided we divide 1 out, okay? So our du will come into play to take the place of 3e to the 3x dx, all right? So 1/3 times the integral of cosine of u du. Okay, and now we have to integrate the function cosine, which if we use the formula that it's on the first page, right, we are going to get that the integral of cosine, keep the 1/3, is positive sine plus c. And at this point, let's just go back, substitute for u. In this case, keep in mind that u was a quantity e to the 3x. Plus c. All right. So that's one. That's another example. Let's look at letter F, secant square of ln of x divided by x. Okay, this looks like all over the place, right? There's lns, there's rationals, there's secants and squares. Okay, let's see how is this going to work. I'm going to rewrite the integral as secant squared of ln x times 1 over x dx. In other words, notice the invisible 1 multiplying secant, right? If we group that 1 with this x, that's the 1 over x that we have here, right? There's a reason why I'm rewriting it that way. And the reason is because in this case, 1 over x, right? Do you see this? 1 over x is the derivative of ln x, right? So that's going to work as our u. So u equals ln x, okay? And du, it's 1 over x dx, okay? So let's do the substitution, okay? So u will take the place of ln x, right? And du will take the place of 1 over x dx, okay? All right, now let's rewrite this in terms of u, integral of secant squared of u du, okay? And the integral of secant squared, it's one of those direct formulas, right? The integral of secant squared is tangent, because if you take the derivative of tangent, you get secant squared, All right, so this will be tangent of u plus c. And let's just back substitute ln x. All right, so that's another example. Okay, let's look at letter G. Okay, so for letter G, okay, for letter G, what are we going to have? Well, notice we are going to have like multiple chain rules going on, right? Something like this. So let's see how is this going to work. Okay, so let me rewrite this in the following way. So sine of 3t, the whole quantity to the fourth power times cosine of 3t dt. Okay, so we are going to set u equals sine of 3t. Okay, du will be the derivative of sine, which is cosine of 3t dt. And in this case, notice how the differentials match. However, we need a 3 here, which is the derivative of 3t, right? So in this case, there's something else we may need, right, to add. That is one factor of 3, right, that we don't have, provided we divide one outside of the integral, right? So let's see. U equals sine of 3t. Okay, so u will take the place of sine of 3t. And du will take the place of 3 cosine 3t dt, which is this whole thing that I'm highlighting here, right? Now, 1/3, let's write this in terms of u, 1/3 u to the fourth power, and then du, okay? And again, we're going to need the general power rule, u to the fifth divided by 5. So we just multiply these guys plus c. And here we only need to multiply across 1 times u to the fifth is simply u to the fifth, and 3 times 5, it's a 15 in the denominator, or 1/15, right? And then plus c. And let me just back substitute for u. And this will be sine to the fifth power of 3t plus c. Okay, and that's another example. All right, let's look at letter H. Letter H, well, what are we going to have? So typically when you set a u/du substitution, you typically look for the most complicated part of the integral to be your u, right? And determine whether the rest of the integrand, it's potentially the derivative of what you choose for u, right? For example, if we look at this, let me highlight this, 3 sine of x plus 5. Okay, pretend the number 3 and the 5 are not there. They're just numbers, right? We would end up with the sine function only, but the derivative, which is cosine, it's right here. So it looks like the u du substitution is going to work, right, for the denominator. That is, we are going to set u equals 3 sine of x plus 5. Du equals the derivative of 3 sine is 3 cosine. And the derivative of 5 is just 0. All right. Notice how this is going to work nicely, except for one factor of 3 that we wished we had, right? Which is right here. We can put that 3 provided we divide one outside of the integral, right? So So u will take the place of the denominator, 3 sine of x plus 5. Okay, let me highlight. And du will take the place of 3 cosine of x dx. Okay. All right, so let's do that replacement. Let's change a variable or substitution. 1/3 times the integral of the u divided by u. But what's the integral of the u over u? In other words, 1 over u, it's the derivative of what function? You might remember that's one of the special ones, 1/3 ln of u. Okay, plus c equals 1/3 ln of 3 sine. Let's just go back, substitute for u, 3 sine of x plus 5, parentheses or absolute value bars, and plus c. Okay, and that's all we do for this one. Okay, let's see what happens. All right, let's keep going with this. Letter I is very similar. Again, observe the denominator, the quantity inside of the radical, 5 plus sine. If we take the derivative, what are we gonna get? Cosine, right? So let's choose our u to be 5 plus sine x. The du will be then the derivative of 5. That's just a number. That's going to be 0, right? So the derivative of a number is 0. And then plus the derivative of sine, which is cosine of x, right? dx. All right, so let's do the substitution here. Okay, so notice in this case we don't need any factors to compensate anything, right? So let's set u to take the place of 5 plus sine x, right? And du to take the place of cosine x dx, right? That is right here. All right. All right, so let's see. So we will have the integral of du divided by the square root of u. All right. However, in this case, we cannot just take the integral while the variable is in the denominator. So here, first of all, we need to play with exponents. So let's replace let's change the radical form into rational exponent form. That's u to the 1/2, right? And then we are going to move this to the denominator because we cannot integrate it while it's in the denominator. So we move it to the numerator rather. Okay, so that's going to be u to the negative 1/2 du. And here we are ready to use the general power rule. This will be u plus to the negative 1/2 plus 1. That's going to give us 1/2 and divide by 1/2 plus c. All right, over here, this is going to look a little bit weird. This 1/2 in the denominator dividing by a fraction is the same as multiplying by the reciprocal. All right, so this will be 2. I'm going to change to radical notation, 2 square root of u. Right, okay, this is too far. Okay, 2 square root of u plus c. All right, and again, let me highlight this u just so you can see how that 1/2 becomes a u. When we dividing by a half becomes a u. Okay, and let's go back substitute for this, right? So that's going to be 2 times the square root of 5 plus sine of x plus c. All right. Let's do another one. Letter J. Letter J, we are going to take the same u. U equals 5 plus sine du will be cosine dx, right? Again, highlight. U will replace 5 plus sine rather, and du will take the place of cosine x dx. Okay, so let's highlight that as well. All right, so this will be the integral of the fourth root of u du. All right, however, we cannot integrate this function while we have radical form, so let's change this to rational exponent form, that is 1 over 4. And let's use the general power rule. So if we add 1 to this, right, that's 1/4 plus 1 divided by 1/4 plus 1. What do we get when we add 1 to 1/4? This is going to be 1 plus 1/4, that's 5/4. Divide by 5/4. Again, dividing by 5/4 is the same as multiplying by the reciprocal, which is 4/5, right? Hopefully that doesn't look weird. Yeah, that's just reciprocals, right? Times, I'm going to go back to radical notation at the same time. That's going to be the fifth root. Wait a minute, no, not the fifth root, the fourth root of u to the fifth. And now that we have everything back again into radical form, let's go back substitute. So 4/5 times the fourth root of 5 plus sine of x to the fifth power. All right? Whole thing plus c. Okay? That's our final answer. Letter K. All right. Notice here the denominator, right? 1 plus secant. If we take the derivative of 1 plus secant, right? The derivative of 1 is 0. The derivative of secant is secant tangent, right? Now try to do it the other way around. If you try to do it the other way around to differentiate secant tangent, you will have to use the product rule, right? And it's going to give us a huge expression. So we don't have that huge expression to work as the du. So that's why we take as our u the 1 plus secant of x, right? And du will be secant of x tangent of x dx. Okay, so let's highlight whatever u is going to take the place of, in this case 1 plus secant x, and with purple we highlight whatever du will be taking the place of, in this case secant tangent x dx. Okay, so this will be the integral of du over u. All right, and what's the integral of du over u again? That's ln of u plus c. All right, just going back, substitute. What are we going to get? ln of 1 plus secant of x plus c. All right. Let's look at another one. All right, sine of the square root of x over square root of x. Okay, I'm going to rewrite this one right here, okay, because if you look at this radical, right, sine of square root of x, the derivative of square root of x will be some radical in the denominator that happens to match here, right? All right, let's see. I will show you what do I mean by that. So first of all, I'm going to rewrite this. Let's see. I'm going to rewrite this as sine of square root of x. All right. Sine of square root of x equals, times 1 over square root of x, right, dx. Okay, so let's take our u to be the square root of x. Well, in this case, let's change this to rational exponents, right? Du will be 1/2 x to the negative 1/2, right? Subtract 1 from the exponent, multiply by the exponent, right? That times the x. Okay, so this is going to be a mess with the negative exponents and whatnot, while originally we were having radicals. So let's change this to du equals to x to the 1/2 dx. And then finally, 2 root of x under 1 dx, okay? Now, how is this u substitution going to work? So number one, highlight this u that will take the place of square root of x. Now, observe this du, it's 1 over 2 root of x dx. Here we're missing that factor of 2. All right, we're missing that 2. We are essentially multiplying by 1/2 inside, so provided we multiply a 2 outside, right? Now let's replace our du, okay? And this is going to be our du, okay? Now, this is 2 times the integral of sine of u du, all right? And the integral of sine again is 2 times negative cosine of u plus c. Let's just go back, substitute. Negative 2 cosine of the square root of x plus c. And this is final answer to this problem. All right. Okay, let's do one other one. Letter M. Okay, now on this last couple pages, this last page, we are going to work on what's this called? Definite integrals, right? Okay. So number one, let's integrate cosine of 2x from pi over 8 to pi over 4. All right, so in this case, our u will be 2x, and our du will be, take the derivative of 2x, that will be 2 du, okay? Now, it turns out, let me rewrite this. This will be from pi over 8 to pi over 4. Cosine of 2x dx. Okay, so I would need a 2, provided we divide 1 out at 2. Okay? Okay. However, when we do the substitution, let's see. So u will take the place of 2x, right? And du will take the place of 2. Oh, by the way, this is supposed to be dx, not du. Okay. This is supposed to take the place of the u, right? So let's highlight this to the x, all right? So when we do the substitution, that is the change of variable, in other words, when we do a u substitution, guys, we are, in a way, we are moving our integral given in the world of x, we move it to the world of u, right? To solve the problem in a way more easy way, right? And then once we solve the problem, we go back to the original work by doing the back substitution. However, when we do the substitution, and I think we have done this before when we covered the improper integrals chapter and the integration by parts chapter, right? If we change the integrand to terms of u, we also need to replace the limits, right? So what do we mean by this? So this pi over 4, right? Let me use a different color to highlight. I'm going to use green, all right? This will become a new limit, right? Using the substitution u equals u of pi over 4 by substituting 2 times pi over 4. And that's going to give us pi over 2. Okay, so the new limit will be pi over 2. And then if we change the lower limit as well, pi over 8, we should do u of pi over 8. All right, this will be 2 times pi over 8. Where did I get this 2 times pi over 8, this 2 times pi over 4? We got this from the substitution, right? That means all the x's, right? Not just the variables on the integrand, but also the limits, because these limits, pi over 8 and pi over 4, are limits in terms of x. So we need to change those to terms of u. And 2 pi over 8, that's going to give us pi over 4. All right. So let's integrate cosine. 1/2 cosine of u du from pi over 4 to pi over 2. So this will be 1/2 sine of u, evaluated from pi over 4 to pi over 2. Okay, in this case, no plus c, right? No plus c in this case. So what are we going to do next? So let me continue over here. This is 1/2 times sine of upper limit, which is pi over 2, minus sine of pi over 4, which is a lower limit. Okay, let's use, in this case, it is your choice to find the values of the trigonometric functions, right? We know sine pi over 2 from either source, right? Sine pi over 2, it's going to be 1 minus sine of pi over 4, which is the square root of 2 over 2. Okay. And in this case, we can leave it like this. I mean, maybe you want to, I don't know, combine these together, distribute, but I think this is fine. On the exam, you will be expected to come up with an exact answer like this, not decimals, okay? So, let's see. Let's do letter N, another definite integral, right? So sine and cosine, how are they related? Well, cosine is the derivative of sine, so if we take u equals sine, the u substitution should work in this case, okay? So u equals sine of x, du equals cosine of x dx, all right? Now, let me move this a little bit lower. Nope. So, if you notice this is going to work has the u du, so u will take the place of sine, and du will take the place of cosine. Okay, now when we change the integral in terms of u, right, we need to also change the limits. Okay, well, here I'm gonna run out of space, so that I'm not gonna do this the same way I did it over here, right? The same way I did it here. I'm not gonna do that. I'm going to write it down right next to here, actually below this. So never mind, let's move this up here. Okay, so we are going to u of the lower limit, which is 0, and evaluate it in the sine function, which is u, right? So sine of 0, and we know from the unit circle this is 0. And then u evaluated at the upper limit, which is pi over 2, that equals sine of pi over 2, right? And in this case, sine of pi over 2, we know that's 1. So the new limits are 0 to 1 instead of 0 to pi over 2. And e to the u, the u, right? So what's the integral of e to the u? Itself, e to the u, evaluated from 0 to 1. Something you might have noticed when it comes to when it comes to integrating, I mean, it looks like takes the set of the u, and changing the limits, all that takes longer than evaluating the integral itself, right? So that's what we do, all this substitution to do the integral in just a couple steps, right? E to the first power minus e to the 0 power, right? What is going to be the answer to this? E to the first is simply e, and e to the 0, any quantity to the 0 power is 1. So e minus 1 is the final answer to this problem, okay? Let's see, all right. Okay, if you will, change to u, and this is purple, right? Just so you can keep track of the color coding here. Let's do another one. Let's do the last one. Okay, a couple more to go. Okay, and so notice again, 1 plus sine t has cosine t as its derivative, so that's going to be very, very helpful for taking u equals 1 plus sine t. So du will be cosine of t dt. Okay. So let's rewrite the integral, right? Let's skip the limits for now. And this is going to be e to the u du. How come? Well, because u will take the place of 1 plus sine t, which is right here, right? u equals sine 1 plus sine t, and then according to the second part of the substitution, du equals cosine of dt, so du equals cosine of t dt, right? Now let's change the limits. U of the lower limit, which is u of pi over 2, equals 1 plus sine of pi over 2. And what do we know about pi over 2? Sine of pi over 2, that's a 1. Okay, so 1 plus 1, that's going to give us 2. Okay, and then u evaluated at the upper limit, 3 pi over 2. This is 1 plus sine of 3 pi over 2. Okay, in this case, 1 plus sine of 3 pi over 2. Sine of 3 pi over 2 is -1. So 1 minus 1 is going to be 0. So the limits are going to go from 2 to 0. Yes, I know the lower limit looks larger than the upper limit. That's very common when it comes to doing these substitutions, right? But don't worry, at the end we are going to get a nice number, okay? I think. So the integral of e to the u is simply e to the u, right? Evaluated from 2 to 0, okay? Plug in the upper limit minus plug in the lower limit. Okay, what is e to the 0? E to the 0 is 1 minus e to the second power, simply e to the second power. That's final answer here. All right. All right, find the area under the curve of y equals sine of 2x. Okay, so finding the area of that graph. All right, so if we graph sine, right, you can use your graphing calculator. Y equals sine 2x, right? You will get something like this, okay, in which the period, one period is pi, half a period is pi over 2 for this. So we will be evaluating this area that I'm highlighting in green, right? So this area, it goes from 0 to pi over 4, right? Use your graphing calculator to get this, right? And that's the area that we are calculating. All right, so the area under the curve, it's only the integral from a to b, right? The limits of integration of the function that we want to find the area under, right? So in this case, the integral from 0 to pi over 4 of sine of 2x dx. Okay, so let's do our u substitution. So u equals 2x in this case. Du equals to dx. So we need to change the limits of integration. U of 0, the lower limit, equals 2 times 0, just the same way we did it on the exercise above, right? And u evaluated at the upper limit to change the limit of integration. That's going to be 2 times pi over 4. Okay, so 2 times 0 is 0, and 2 pi over 4 is the same as pi over 2. Okay, so we are going to integrate. All right, so u will take the place of 2x, right? That is. Let me write it down so you can keep track of this. So u equals 2x, right? That's where the substitution comes from. And by the way, it looks like I needed a constant here to provide. We divide 1 out, right? Multiply by 2. Okay, divide by 2. And du will take the place of 2dx, right? So du equals 2dx, all right? Now, the integral of sine, first of all, it's going to be negative 1/2, okay, because the integral of sine is negative cosine of u plus, and not plus c, in this case evaluated from 0 to pi over 2, forgot to write the limits, and this is negative 1/2 times cosine of pi over 2 minus cosine of 0. All right, so what are we gonna get? Negative 1/2 the cosine of pi over 2 We have that from either the table from a couple sections ago or the unit circle. Cosine pi over 2 is 0 minus cosine of 0, which is 1. Okay, so 0 minus 1, it's going to be negative 1. Negative times a negative is positive 1/2. All right, so 1/2 is the area under this curve. All right. Okay, let's look at the last page. The last page is a double integral involving trigonometric functions, right? All right, so the first integral will be done with respect y, right? Okay, let me highlight sine y dy with the inner limits and the outer integral will be with respect x, and we'll take the limits from 0 to 2. Okay, so let's use the notation I used on the last section of chapter 8, by the way, right? So the integral from 0 to 2 times the integral of from 0 to pi over 2 of x sine of y dy times dx. Okay, now because this integral is with respect y, this x, I'm going to write it outside of the integral, right? So let me write this down, the whole thing again. This will be the integral from 0 to 2 of x times the integral from 0 to pi over 2 sine of y dy, all right, times dx. Okay, so let's integrate sine of y. In this case, no use the u substitution because the derivative of y, which is the quantity inside sine, it's simply the derivative is 1, so no need to do a u substitution. So this is going to be the integral from 0 to 2 times x, which multiplies the integral of sine, which is negative cosine of y, right? Evaluated from 0 to pi over 2. Okay, dx. So let's evaluate the inner part first, and this is going to give us the integral of 0 from 0 to 2 of negative x that multiplies cosine of pi over 2 minus cosine of 0. Okay, let me move this a little bit to the left. Okay, and that times dx. Okay, so let's evaluate cosine of pi over 2. Cosine of pi over 2, according to the unit circle or the table, depending on, or triangles, whatever you want to use. Okay, that's going to be 0 minus cosine of 0, which is 1. Okay, and then 0 minus 1 will be negative 1, and then that negative x, that's going to give us the integral from 0 to 2 of positive x dx. Okay, so let's integrate x dx. So this will be x squared divided by 2 from 0 to 2. All right, so let's plug in the upper limit. 2 squared divided by 2 minus 0 squared divided by 2. Again, what are we plugging in? Upper limit, right? Upper limit minus lower limit, right? Lower limit. Okay, just the same way we did it here on the previous integral. Upper limit minus lower limit. lower limit. Okay, so the last term will become 0. Then we were going to have a 2 squared, which is 4. Divide that by 2, and that's going to give us a 2. Final answer. Okay, so guys, this is the end of the section, and at the same time the end of the chapter, right? So here is where we conclude the chapter, and soon we will be working on the next chapter, which is infinite series and sequences. All right, okay, so see you in the next video. Bye bye.